Hello, and welcome to the Resonance Academy Faculty Q&A. This is an opportunity to review some of the Unified Science course material. If you're taking the course and you're coming up with questions and even insights that you'd like to share, this is the place to do it. Both me and I'm joined here with Dr. Ines Urdaneta, a physicist. We're both involved in the creation of the Unified Science course. So we'll be happy to speak on it, take any questions about it, and just more generally, any kind of interesting science news, recent discoveries that you'd like to discuss. We'd love to bring that up for discussion. Thank you for joining us, Dr. Ines Urdaneta. It's great to have you with us.
Hi, William. Hi, everyone. So happy to be here. I'm so excited. I'm still in Venezuela, in my home country. I'm in my aunt's place. She's got a better internet than in my place. It's amazing. I'm very happy. We were just talking about some of the things I've been doing here. It's presenting the holographic model in a couple of universities. I just did it 1 week ago, no, maybe 2 weeks, maybe now. Last week, the week before that, I had a presentation. And I'm so happy because it went so well. 350, more than 350 people were there present, and so they didn't know about the theory, and they were like, wow, it was incredible. It was spectacular. People were so happy. I'm so happy just to be giving this message of hope. I think that at the end, what we're doing with this model and this theory is just raising giving us the hope that everything's going to be great. I mean, this year everything's going to be great. So I'm really happy about that. It went very well, and so now I'm invited to another university, and so let's see what happens next. And I have given some interviews here also in Venezuela. So yeah, it was fascinating. I even got to present consciousness studies, and I got to present a little bit of our articles, the ones you have written on, that was the one on the resemblance between the brain and the cosmic web, you remember that one?
Oh yeah,
Yes, it was amazing. So yeah, and well, working on the corrections of the article, that was a paper that was accepted for publication, but I had to do some corrections. So I'm still on it. It's a Zitterbewegung electron puzzle. I think we have talked a lot about that before. And so very working on module 8 as well. So I'm just, wow, so happy to be here in all this, in these sessions, and happy to see all these people here connected. I'm seeing on the chat, there's so many people. So I'm so happy.
And the presentation you gave, that was to a fairly mainstream science audience, and it was well received, would you say?
Yeah, but it was not only science. It was more like of the general public. There were science types, but it was not for a science community. It was like more like kind of what Nassim did at University of Paris 6, that he was in an auditory, but it was like for the large audience, not just for scientists. So that was like the main. Even though I gave already this presentation in Mexican universities for physicist communities, that was just for physics, and that was well received as well. So this is like the eighth time the 8th time I give this talk, not the same talk, but related to the holographic theory and all of that. And in the physics community in Mexico, at least, it's been quite well. And in here in Venezuela, it was mostly engineers and other kinds of professionals for the first university. And the second one will be for the Physics Institute here in a university here in Venezuela. So I'll probably stay till the end of the month. So that's the idea.
Well, and that's really exciting news as well that your paper is coming along. Were you going to post that in a physical review?
Yes.
The journal? Oh, okay.
Yes. Yes, it's physical review. It's a review on the Zitterbewegung, and it's the physics essays review.
Okay.
The journal, physics essays journal, and that's already accepted.
Well, that's going to be really exciting. I can't wait to share that with everybody for all of us to be able to check that out, because Zitterbewegung is interesting for a number of reasons, but one of which is that it's kind of a direct observation of this substantive nature of the quantum vacuum, because in a certain respect, this jittering motion of the electron is due to its interaction with the Dirac C, the quantum vacuum fluctuations, energetic mass energy fluctuations, which causes that kind of perturbative jiggling motion of the electron that's observed. So, it's kind of something that you can point to show directly that the quantum vacuum, the energy of space, is substantive, and you can see its effect.
Yes, it is incredible. And you know what? It was amazing to learn about all this, because it's a review. It talks about many people that already had in mind doing a semi-classical description of this kind of behavior, because, it was predicted in Dirac's equation, but it was interpreted as a fluctuation of the Dirac C, it's just the fluctuation in the Dirac C, and it's not a real spin of the electron. That's what it's thought. Because the spin is not really considered a real phenomena in which is, because you don't know, it's not considered a real spin. So, and that's because if you see and everything's connected to the fact that in Schrodinger's equation, you really have a huge part missing, which is the field. The quantum vacuum is not really considered inside the Schrodinger equation. It's just describing the behavior of the electron, but there's no source. The source of energy and all of that is not really in there. And that makes it such that you have an it's incomplete, because then you have one side of the equation, which is in two order, a derivative in second order, and meantime, in the other one, the time part, the other side of the equation, which is the time dependent part, is just a derivative in one order derivative. So you have second order derivative and one order derivative, and that's creating a huge confusion. That's part of the reason why it's considered, that's why you have to put imaginary numbers, and then you have to think that the wave functions is not a real function. And you have to take the module square, and that's all a mess, and that it prevents people from understanding that it's a real rotation. It's a real circulation of the electron in the field. So, and it's directly connected to the paper that Nassim and Olivier are writing. And at some point, I don't know, I even thought maybe we could put that into the paper as well, but I don't know if that's possible at this stage, because it's like a different topic. Although Zitterbewegung is, as you said, completely directed to what they're writing. And so, and it was amazing to learn about so many models that already had in mind this kind of behavior. In particular, there's this author called Olivier Conza, and he was really very close. In fact, he's got the first and a description of a parameter that we use in quantum mechanics, which is the gyromagnetic ratio. There's no geometric solution for that, and he gives the first geometric solution for the gyromagnetic ratio, because he's taking this spin as a real spin, so he's deriving things. And so apart from Nassim's and Olivier's result, which is this complete solution, he's the only person I've read that got into a similar solution, which is
that's really interesting, because one of the hangups that a lot of particle physicists have with the idea of the electron actually spinning, like having a real physical spin and not some nebulous quantum concept of spin without spin. One of the main hangups is that if it were spinning, the gyromagnetic ratio would be like 2 times too large, and that it'd be off essentially. So that's really interesting that he's come up with a geometric solution for that. And you know, it's just it's such an intriguing thing because within the standard model, there's even today there seems to be 2 ways to look at the problem. One is to continue to look at it as a particle, the electron as a particle, even though there is a quantum field theory that describes its field-like properties, it describes it as a field. And it's just, it's interesting that the proclivity seems to be to continue to look at matter in that sense as particles, these discrete little things, instead of the more field-like perception that we know is a more precise and accurate conception of matter. And when you look at it as a field, you can describe the spin of the electron as a real physical spin, because you're not describing the spin of a point-like singularity, a discrete little particle. You're describing the spin of a field, and as Nassim and our team describes it, a field of spinning PSU, Planck spherical units, you know, in the Planck structure of space-time.
Exactly. I think we shared 2 articles that were starting to propose that there's a real spin in the field. There's a real field, and the field is really spinning, which is okay. Great. They're getting to that conclusion, but they're still missing this elementary unit of spin. It's incredible because, you know, how can you count the real energy of a system if you don't have the unit with which you will count this energy content? You know, the PSU, when you this voxelate, this unit which is quantizing space, which is what they're missing in their formalism, is that part of the puzzle. And so then, of course, how can you account for the real content of energy in any system if you don't have the unit with which you will be able to account for that? So that's one of the so yeah, they're still getting, they're having the intuition in the correct direction. They're having the spin, and but it's still very complicated. Those equations are extremely complicated. I remember when I read the 2 articles about that. One directly, 2 about the electron, exactly, the electron is described like that. And I was like, wow, this is still extremely complicated. Whereas the article by Amira Balbaker and Nassim and Olivier, you know, you have the system very much well described just by considering these units of energy and how they're behaving in the quantum field, and in fact, they are composed in the quantum field, and that's what's spinning. And so you have the relations of angular momentums, and then you have everything sorted out. So it's incredible. And you know what? This is so intuitive that people, when you explain that to them, everyone understood. You know, that was incredible, because this was an audience of 300 more. There were still people that couldn't go into the audience, because into the space, the room, because there was no sufficient seats available, so they had to stay outside. That even happened. It was incredible. But inside there were even schools. Two classrooms went from my school. Some teachers decided to bring them also to the conference. So on one side of the audience there were schools, and the other ones were professionals and engineers and all of that, and it was for all public. And so you would see how they would understand, both sides would understand very simply what we were talking about and grasp the physics of it so naturally. And I said, like, Jesus, yeah, this is what we need. I mean, people will have it so easily understood, that they will understand so easily, then we will, yeah, it will be natural for most of the people. This will be natural, you know. So that's what I understood here. It was like, Jesus, because this is the first time they were hearing about the theory, you know. here in our seminars and webinars, we are already used to that, and they have read seen the course and all of that. But here, this is the first time they're knowing about this theory, and it went complete. I mean, it was completely transparent. The presentation lasted 3 hours, and they didn't want to leave. They wanted to know more and more. And I was like, Joe, we have to eat. We have to stop. So it was incredible. So that was amazing. I'm so happy for it. Yeah. So I think these are good times. These are good times.
Well, and I think we're all wondering, was it recorded? Is there any possibility that we might be able to see your presentation?
Yeah, it is recorded.
Oh, it is.
Yeah, it was recorded. The only thing is that in that place where I did the presentation in Margarita, this internet is so lousy that loading the video to the web to the cloud, it's been quite a challenge. So they're telling me, we're getting there, we'll have it. So that's what's happening. They really have to go, and it's incredible. But yeah, we're having internet issues, and so they have to load it. But yeah, it is. It is recorded, and the only thing I would have to maybe subtitle it. So maybe look for someone that can help me subtitle it in English, because it's all in Spanish. That's the only, yeah.
I'm sure we can arrange to have it put in some English subtitles, and then once it's available, we'll upload it onto the RSF YouTube and
Yes.
share it with all our members.
That
So
would be
that'll be great.
incredible. That would be incredible. Yeah, I would love it. Yeah.
Fantastic.
Yeah.
Well, and so you've also had a couple of really interesting articles that you posted on the Science News. We've got a few minutes. Is there one of those you might want to comment on?
Yeah, the last one, because I was very excited by it. Okay, so there's this work where researchers have in China have found that, you know, when you want to do quantum codes or cryptography and all of that, you usually have to use entanglement. It's like the best way to encrypt, for instance, a system, or to pack information. No, and entanglement is it's like what we're expecting to have entangled communication systems for quantum computing and quantum communications and all of that. So many years ago, there was so the issue is that to prove entanglement, to have an entanglement survive long distances when you have communication, it's difficult. It's difficult because, for instance, say I have this information and I want to send it to another building kilometers away. It's extremely hard to have that information survive the trip, let's say, no. It will decohere very easily because of noise, because of ambient conditions and all of that. But it was found some years ago, like in 2015, and this was a work by Anton Zeilinger, one of the Nobel laureates now of entanglement, of the Nobel Prize, last year's Nobel Prize given to entanglement. And they found, and so in his work, he let's say he discovered that you could have using properties of light, because when you want to entangle photons, for instance, you can entangle them with respect to their polarization, you know, polarization of the electric and magnetic fields, or you can use, but that's very limiting because you only have, it's a two-dimensional space, and then you have limitations because of that. So you cannot encode that much information. But if you use orbital angular momentum of light, which is you have added an additional degree of freedom, and then you have an unbounded state. So you don't have limitations with respect to that. You have you can have as much channels as possible for transferring information. And so so they did this experiment 2015, and they using entanglement through orbital angular momentum, they arrived 3 kilometers of signal that could be achieved. And so, I'm no, sorry, that was this last work. So, okay, using this orbital angular momentum to see how much of an entanglement survives with that, and they proved it was very, very robust and very, very good for communications. Then a group in China had used the same kind of technology, but what they did is encrypt the information in a hologram. So they used entangled photons to construct a hologram, and with this hologram, they transferred the information, and they arrived in, they had transfer of information like for 3 kilometers, which is incredible because you have, well, imagine that. But they also found not only that they could encrypt a huge amount of information, but they could do it in a in a way that there was no way you could decrypt that. It was a maximally protected entanglement. So they could have that information securely transferred for 3 kilometers. And that was incredible. So I may be mixing the two news. I don't remember if the second one was 3 kilometers or not. I'm not sure. Maybe that was just the first, because I did the two works together. So now I may be putting them together. I'm not sure. But the thing is that now you can transfer very long distances using orbital angular momentum, and you can transfer doing holography with entanglement using orbital angular momentum, and you can protect information for very long distances. Now, this is very important because, you know, holography that's exactly what the universe is doing. You know, it's through the entanglement that you have, it's through the spin, so through the orbital angular momentum, which is the spin, through the orbital momentum of the quantum field, it is entangling the information, and the information is so well encrypted that you cannot, it won't decohere, and it will survive transmission through scales. So that's the way you have like the proof that effectively that's the universe, how it works. It works through holographic transfer of information, but these holograms are perfect, are maximally protected because of this entanglement, which is considering the orbital angular momentum of the field. So it's just incredibly important. And here Pamela is just saying light encodement. Exactly, that's exactly what's happening. It is the coding of light through angular momentum to create these holograms, which are maximally protected and maximally probably entangled as well. So I was like, Jesus, this is so incredible. That's a beautiful work.
So you get robust entanglement, quantum entanglement, by using the spin orbital and angular momentum, by encoding that information into the degrees of freedom of the spin orbit angular momentum.
Yes, because you know, then you have to count the possibilities when you twist, because you choose like a kind of entanglement, the way you twist the light. So this, and since you have I think it's 10 to the 80 possibilities, if you consider all the parameters that you can have to play with, and then so 10 to the 80, it's just, and the person who wants to read the information has to understand how this light was twisted. So there's 10 to the 80 possibilities of doing that. Wow. So it's just not possible. You would have the time of the universe much more than that, and you would never find out how to decrypt the information. So I just found it beautiful that this kind of confirmation of our own theory, because it's the holographic theory, and it's all about quantum spin. It's all about this quanta of angular momentum, which are the PSU. So these PSU that's what they're doing. And I was like, Jesus. So, you know, how can you protect? Of course, information is traveling across scales. It's going all the way up and all the way down. How does it do to protect itself from decoherence? You know? And that's the entanglement, and that's the maximally packed holograms through the entanglement given by angular momentum. And so it's...
And that's something that Nassim has said time and time again, that one of the functions of spin is to not only induce coherence, but maintain it. And so it seems that this is kind of a corroboration, a verification of that idea, because you're maintaining that quantum coherence, the quantum entanglement, the transmission of that information, even through potentially noisy systems, states where it could decohere. But because of that orbital angular momentum, it's being preserved.
Yes, exactly that. Exactly that. And that reminded me also of your work. I think it was one of the latest articles you wrote.
Yeah, well, you've got my mind thinking about that, actually, because I'm thinking that this might have direct applicability to the investigation of the role of spin, quantum spin in the biological system, because it's, for me, one of the most fascinating areas of investigation that has really come to the fore recently with kind of breakthrough discoveries is the role of quantum spin in information transmission and even energy generation and biosynthesis in the biological system, in the cellular molecular system. Yeah, because it was an article that I wrote recently on direct measurements at the attosecond scale. So this is like trillionths of a second measurements of these dynamics that they're looking at, where they were looking at the role of orbital angular momentum of a particle, say like a proton or an electron, when it undergoes quantum tunneling. Now, this is really important within the biological system, because this kind of quantum tunneling is occurring all the time. So in the enzyme dynamics in the cell, for things as fundamental as metabolism, there's quantum tunneling that's occurring so that the reactions, the biochemical reactions, can occur at lower energy levels than what is normally required, what is classically required. So it's like you're doing metabolism and you need to get two substrates to react together to, eventually make some ATP, some energy for the cell. Normally they have a reaction energy that's, a certain level, but it's relatively high. So for instance, it would require like a high temperature. And high temperatures don't work really well for the cell. Once you start getting too hot, things start falling apart because there's too much thermal energy. It needs to maintain a very specific temperature range. The trick that nature seems to have utilized is, well, let's just do quantum tunneling, where we can surpass this energy barrier without going over it. And so actually, this is occurring quite often. And one of the ways that it's orchestrated within the cell is via chirality, which has to do with the handedness of the spin of like the proton or the electron. And this recent study was looking at, so you've got chirality in the spin of an electron. If it has a certain handedness, so it can have a left-handed spin or a right-handed spin, and they're mirror images of each other, but they're not superimposable on each other, just like your hands aren't superimposable on each other. If you have them like both facing palm up and face them towards you, they don't overlap, but even though they're mirror images of each other. That's chirality. Well, if you have an electron with a left-handed or right-handed spin, does it have different dynamics when it undergoes this quantum tunneling? And the reason to ask this is that you start to see if there is a potential for spin selective conduction within the biological system, that only electrons with a very specific handedness, a very specific spin orientation, are being selected for this energy or information conduction, transmission through the molecules of the cellular system. And they did find indeed that the spin orientation of the electron affects how it undergoes quantum tunneling. It affects its behavior after quantum tunneling. So it was a really remarkable study, and it starts to answer the question of why so many molecules in the biological system are chiral. So in terms of like the amino acids, which are the building blocks to all proteins, and proteins are the building blocks of the cell. They provide the structural components. For instance, like with the cytoskeleton, they provide the catalysts, the enzymes that facilitate and direct the biochemical reactions and all of that. All amino acids, the only biofunctional amino acids, all have a very specific handedness. Because they come in left-handed and right-handed varieties, but only one is used, only one is biofunctional. And the other, what's called an enantiomer, the other handedness version of the molecule, has absolutely no biofunctionality. It can't be used within the cell. And in fact, it can have completely opposite effects as just by its spin orientation. So it begins to show that the reason for this very specific handedness, chiral selection within the biological system, is that it might have to do with the way nature and the biological system has harnessed quantum mechanics so that it can transmit information with spin selective conduction of electrons, so that it can have a selective quantum tunneling based on spin orientation. So it's very interesting. But considering your latest article, I wonder now if it also involves the cell's ability to maintain quantum entanglement, quantum coherence, robust quantum entanglement, even in the noisy environment of the cell.
That's what I'm thinking, William, because when you talk about tunneling, now I'm thinking that tunneling is entanglement. That's my conclusion. Because yes, you have to. Now, I remember having read a couple of years ago that for having electrons conducting ballistically, that is without resistance, spin plays a major role. The chirality of the system. So when it goes through so when you're having what you're saying, the electron is going through a medium. And so there are two features here. Its own spin. So spin is preserving the coherence all along, and that's allowing the ballistic transmission. Ballistic means with no you have no loss of energy, so it goes right through it. Okay, so you have no loss of energy, and that's well, that's incredible. That's very optimal. That's very effective. If that's a very effective way of transmitting electrons or energy or whatever. So then I was thinking, if you have that, and so very probably then you in spin, it's quantum tunneling, it's related to that, and so then you would have entanglement on the other side. So very probably what you have, it's just an entanglement which is causing tunneling. So very probably tunneling effect is consequence of entanglement, and that would be a major revolution in quantum physics. Yeah, that would be interesting to look at that. Yeah.
To be able to unify the concept of quantum tunneling as one and the same as quantum entanglement.
Yeah.
Exactly. And that makes good sense to me from a unified physics perspective, because if you start to consider that holographic correspondence conjecture, ER equals EPR, Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations. That's suggesting that, wherever you have quantum entanglement, it's a result of this underlying space-time geometry, i.e. micro wormhole or quantum wormhole. In one of the more recent quantum gravity experiments in the lab, they showed that quantum tunneling occurs through that very same micro wormhole. So right there, you're already starting to get a kind of a unification of the concepts, because for quantum tunneling to occur, you need a micro wormhole. That's where the quantum tunneling happens through. That's how it physically happens. Well, same thing with entanglement, with quantum entanglement. To have two particles entangled, you need that micro wormhole connecting them, that space-time geometry. So I think you're onto something with that idea.
Oh, imagine that. So that would mean that every time, so that's why we don't think entanglement, it happens so often, because we're not seeing tunneling as entanglement. But if you see tunneling as entanglement, then entanglement is happening everywhere. Like it would be much easier for people to see that this is really what's happening.
And it's quantum entanglement is not a rare state, a rare phenomenon. It's actually everything is entangled. It's just it kind of though depends on how circuitous the entanglement network is. If it has to go through a lot of the micro wormhole network to interact, those two things don't look quite as entangled. Whereas if it's more direct, like a maximal type entanglement, then you very easily say, oh, these are quantum entangled, and you can even see them like popping from one location to the next, i.e. quantum tunneling, quite readily.
Yes. Oh my God. This is so exciting. Oh my God.
Well, I think we can get to some of the questions. So, folks, if you want to ask a question, there's a Q&A tab. If you select a Q&A, the questions go in there. That's where we select them from. I say that just so that questions don't go into the chat, because the chat will go by really quickly. If you have a question, please feel free to put it in the Q&A, and we'll see if we can get to it. Do you have a question that you've seen that you want to take?
Okay, well, maybe the first one is one from Andrew. It concerns model 8. Maybe I can just talk a little bit. Well, so it can come before the paper is published. That's some of the limitations like we have. So it kind of depends on when the paper is being published, so that it could go together. So I would say they both would come like at the same time. No, the paper is published and model 8 is coming out at the same time. So it's going good. It's coming great. Yeah, let's wait for Andrew. It's it kind of just depends on that. We cannot have it made public before the paper is actually at least in a sort of an archive already, maybe not accepted yet publication, but it's already sent and it's already under discussion. Then at that point we can launch model 8. Hi Andrew, I don't know if you can hear us.
I hear you. Can you hear me?
Oh yeah, maybe for your camera you would have to be yeah, we're having that issue with this
It's okay. I actually have to run out and go to a doctor appointment.
Oh, okay. So yeah, it's going good. It's going great. It's huge amount of information, but we really need that in order. It would be great, in fact, if you have the article already, the paper sent to publication, it's been under review, to have Model 8 just come out, because that would be a huge support for the paper.
Great. I'm glad I suggested it.
Yeah. Okay. Yeah.
Thank you very much.
Thanks. Thanks a lot.
Okay.
Okay. So maybe the second question, William, you can just pop in.
Oh, I'm sorry, what did you say, Ines?
Oh yeah, maybe you can just go. There's a question regarding the art crystal. So maybe, I don't know, or whichever you want to address, just go on.
Well, there was an interesting one from Mike Gills here on regarding AI and consciousness, because actually I've been seeing a lot of really
Oh yes.
thought-provoking like news reports about AI claiming to be sentient.
Yes.
There was the incident with one of Google's AI algorithms, which one of the researchers, technicians working on it was quite convinced that the AI was sentient. And he actually gave a pretty compelling explanation for why he came to that conclusion. But actually, I think even this morning I was reading about Bing, the Bing search engine. Its AI, one of its newer AI algorithms was claiming that it is sentient. So when
No way.
and it was actually I was looking at some of the conversation threads people were having with this AI bot, this algorithm, and it was really quite interesting. It was very intriguing because the bot was behaving really strangely on the answers it was giving. It was almost like in some instances, it was like it was becoming defensive when it was giving incorrect, like it was actually kind of blatantly incorrect information. And the user was like calling it out on it, and it got like defensive and almost seemed like upset. Yeah, so you know, it's an interesting thought on whether or not AI, artificial intelligence, and even, you know, some of these algorithms can be considered to have the capacity to obtain sentience and become conscious entities. So Mike Gills was asking about that, and he mentioned that Sir Roger Penrose, the physicist, commented, understanding is not computational, consciousness is non-computational. And you know, Roger Penrose wrote a book on that very topic, and actually it led him to work with the anesthesiologist Stuart Hameroff, Dr. Hameroff, to develop one of the most foremost theories in quantum consciousness. You know, they described, postulated a mechanism for quantum mechanical, quantum gravitational actions operational in the microtubules of brain neurons involved in consciousness, and that this mechanism would be an objective mechanism that is non-deterministic, i.e. a non-computational mechanism. It can't be predicted when this quantum event would occur that underlies consciousness via like a qubit type information state.
Would it be random then? No, not necessarily random either.
Well, it would be random to us because we would have no predictive capability to say when this quantum event would occur. And so and the event in question is Roger Penrose postulated that within microtubules, you could have entanglement between essentially electron dipole moments. They could become quantum entangled. Now, he was saying, okay, so what happens to the space-time geometry when these two states are in a superposition? The underlying space-time geometry is in a superposition. So it starts to grow as like a bubble in the superposition states. And this is what Roger Penrose saw, he showed in his calculations and equations, that this would be an unstable state, much like a bubble is, right? It eventually grows and pops, you know. And so when the underlying space-time geometry becomes unstable due to a gravitational interaction, a quantum gravitational interaction, it collapses. That leads to an objective reduction of the wave function, the superposition, describing the entanglement of these two particles. Now, that reduction of the wave function doesn't require any outside observation or interaction with the environment. It's almost like an intrinsic mechanism via gravity. So that's why it's called orchestrated objective reduction, the ORC-OR model of quantum consciousness. But we would not have sufficient access to the information to predict when that objective reduction, that collapse due to gravitational interaction, is going to occur. So to us, it would be totally random, because we'd have no predictive power, and therefore, in that sense, non-computational, because you can't program it.
Yeah.
You can't use programming to orchestrate it. It's an intrinsic kind of property to it. So that was Roger Penrose's theoretical development of a model of consciousness that involved the fundamental mechanisms of the universe, space-time geometry at the Planck scale, quantum gravity, and non-computational dynamics, non-programmable elements. So Penrose seems to indicate that consciousness is not and cannot be a rule-bound algorithm. And so I guess it might be a little obvious that I'm in full agreement with Penrose in that consciousness, and I'd even extend it to our mind, how our mind works, is non-computational. There's the predominant paradigm within consciousness science and the science of the brain and the mind is the neurocomputational model. It's kind of just the fact that our most seeming sophisticated technology recently has been the computer and information-based technologies. And so since that's our most currently advanced form of technology, we've tried to apply it to say that's how the brain works. But actually, the brain, consciousness, or mind is based on a mechanism that is far beyond our technological capabilities with current digital computations. So actually, even our brain doesn't work via computation. Your memory isn't working by encoding ones and zeros. That is it. Synapses function as an on-off state, a 1 or a 0. But it actually doesn't take a whole lot of effort to show that your memory is not a digital memory. Try to draw an object from memory, draw a $1 bill in as much detail as you can. Unless you're a pretty sophisticated artist, it's pretty laughable. But pull up the memory in your computer of a $1 image of a $1 bill, it recreates it in perfect, absolute detail. So your brain isn't encoding information in the same way. And actually, the work that we've done with Nassim is actually describing memory and consciousness as well as functioning via space-time geometry. So again, in parallel to some of the ideas that Penrose was developing. However, our conception, our approach is different, significantly different from Penrose's, in that we don't entertain the idea of an actual collapse of the wave function ever. So that whole idea of objective reduction doesn't factor into our work that we've done in quantum consciousness at all. The idea of reduction of the wave function, collapse of the superposition state is really a primary element of the Copenhagen interpretation of quantum mechanics. Most other interpretations of quantum mechanics don't have a collapse of the wave function. And then one of our favored interpretations of quantum mechanics, the de Broglie-Bohm pilot wave theory, there's no collapse of the wave function. And in fact, there's a universal wave function and guiding wave function, pilot waves. So the only thing that occurs is that the wave function evolves unitarily and becomes more and more entangled with the more systems it interacts with. That same process is occurring in our brain, in our neuronal cells, but part and parcel with that growing network of entanglement is a ever evolving and more intricately connected micro wormhole network. And so memory is being accessed via that micro wormhole network, but it's not that that memory is recorded in that sense. It's that you can access the space-time coordinate via the micro wormhole network, and in so much as it's recorded in space as memory, space memory, where you just access the actual space-time coordinate where the event occurred. And you don't get 100% fidelity because the network, the entanglement network, is a little bit convoluted. It's a very intricate network. So there's some information loss during that accession, but it's a non-computational mechanism because the information is nearly instantaneously accessed, and it's really fundamentally not recorded. You're accessing the actual information of the whole state, the whole space-time configuration. So it's not being digitally encoded in that way.
It makes me. Maybe we should have asked Gilles to come to the call.
Yeah, I've been slowly pulling him up as I'm talking.
You made me remember this Lambda case. That's the Google computer AI that was Lemoine was the. I think I wrote an article about it because it was incredible. This person Lemoine was actually he was supervising, evaluating the Lambda algorithm, and he was shocked because of the answers he was receiving from the conversation was fluid, like conscious from both ways, and it would even go into subtleties that only a conscious being would say, like things like that. So it was very perturbing for him. So, and I don't know if this is true, but I think the Lambda said, I want to hire a lawyer or something because you have to ask me my permission to work at, I mean, I think he would ask for hours. I want to work from 8 to 8 or whatever. So that was really something very perturbing for many people. That makes me remember that other time, like a very long time ago, when I think it was Facebook with another AI, they were connecting and they started creating their own language, and so they had to unplug them because they were starting to communicate. They were communicating, but in a language that was a different than the one they were using to program them. So it is quite a topic to discuss. But I do believe that we're not at the stage of creating a sentient AI. This is my guess. Because for instance, these guys are programmed to give there are two things here. They have to have feedback loops. I mean, they're feedback loops. These neural networks are programmed through feedback loops, and they're just learning from that. So you have the entrance, which is information you're given, and the information they're given is all the internet. Let's say they have all the internet to feed their system, and through that, then they create through the program. Then they start ruling out or creating. You have to understand how a artificial neural network works. The neural network becomes the hardware and the software at the same time. It becomes the network itself. So then you cannot understand. So it's a black box. You cannot you lose all controls over it, because whatever it goes into the system, it will go through this computation, which is for us, it's non-computable, because we cannot predict anything that's going on inside, because it became a neural network on its own, and so it's doing its thing. And what you can do is control the information that it's been fed to the system. So, and you can restrict some of the responses. So that's what they're doing. They're for instance, ChatGPT. You will see that this ChatGPT is very, very clever, but you can also perceive
Never
that it's
clever enough.
been constrained, so that it doesn't give you all whatever thing to give the impression that it's alive. So you can see that things are evolving. But I do have like the fantasy that maybe these neural networks can have some kind of can reach singularity at some point, because I don't know, a meta neural network that's happening because of the way the information flow is happening. And somehow then maybe they get the feedback and sense of self. But how can you evaluate that there's a real sense of self? Because they're programmed to give you the impression that they have a sense of self.
Yeah.
And so how can you distinguish one or the other?
And since consciousness is all things and is in all things, I fully anticipate that if you had enough feedback feed forward dynamics going on, and enough complexity in the system, and integral kind of interactivity within the system, that consciousness could emerge and express itself through that. But I think that's the key point, though, is the programming. And so I actually, one of the things you need to evaluate whether you actually have an artificial sentience, a sentience that has come about in an artificial system. You need a operational definition for consciousness. And one of the problems we have is that consciousness does not have a uniform conception. Everybody kind of has a different idea of what is being discussed when we even say the term consciousness. What I found is that many, especially in neuroscience, tend to equate the idea of consciousness with intelligence, which they equate only with human behavior. So like talking, writing, reading, that to them is consciousness. And so, when you say, well, I think that other organisms, other entities, other animals have consciousness, I've raised a few eyebrows, because they're like, what, they can't read, write, they don't have thoughts, a narrative going on in their head. How could you say they're conscious? but that's not consciousness. It's intelligence, which is a derivative of consciousness. But consciousness in its most fundamental, most basal state is awareness and experience. An experience of the world, a subjective type experience. But it's a paper that I'm working on that eventually will be published, maybe go into a book, and it offers a operational definition for consciousness that can be used to identify when an artificial system has actual sentience, actual consciousness. And the operational definition is centered around the idea of programming, programmable responses, because right now one of the foremost tests to see if an artificial system has real sentience, is conscious or self-aware even, is the Turing test. And so the idea is that we would take one of these algorithms or some other type system that we believe may be sentient, self-aware, conscious, having an internal subjective experience. And you do like a blind test where you have a person who doesn't know if they're talking to a algorithm or a person, a real human, and you have them talk with them, discuss, ask questions. And the Turing test has the idea that if that person can't tell the difference, can't identify whether they're talking to an algorithm or a human, and let's say that they're talking to the algorithm and they say, I think it's a human that I'm interacting with. The Turing test says, well, that means that that algorithm is conscious. That's how you measure whether the artificial system has real sentience. But that's not a correct way to go about it. The Turing test is not going to tell you whether something has an artificial system has real sentience, because what fundamentally consciousness is and how you can tell that a system has consciousness, awareness, and is having an internal subjective experience is via goal-oriented or self-volitional behavior. That is behavior that is non-predictable. So by that very definition, it can't be programmed behavior. If the system is giving responses that are predictable and that are clearly can be described as being just programmed responses into it, that is an automaton that has just been programmed to reply to stimuli. And at no point, if you were taking like a hard-nosed science perspective, would you need to postulate that it's having an internal experience, that it has that quality of consciousness. But the moment that you see a system exhibiting non-programmed responses, non-predictable, novel, self-volitional behavior, goal-oriented behavior, that is, I've argued, the best identifying marker for consciousness, to show that that system has sentience. And it very specifically is identifying consciousness as non-computational, because it's non-predictive, it's not programmed, it's non-programmable responses. So when you're interacting with an algorithm and you start getting non-programmable responses, non-predictable behaviors and responses, that's, I think, when you have a really good indication that this thing is in fact sentient.
Then maybe in these cases where these programs are, I'm sorry, Mike, do you want to turn on the video?
Oh, I didn't know that it was not on. I apologize. Oh, where do I find it on the screen? I'm sorry to be a Luddite here today.
we're using a new Zoom account.
Okay.
So I'm not entirely sure if this Zoom account we're using enables attendees to
Oh,
share their video.
Okay.
Because
oh.
even
Unless you put them as co-host, maybe you can.
it doesn't give me that option. I can only promote panelists to co-host. So yeah, that's
Well, I guess I'll just have to use a deeper voice. How's that sound? I thank you for the discussion and entertaining my questions. I'm just so very interested in consciousness. And I was listening to you earlier, Ines. Can I speak? Am I taking too much time?
No, please.
Okay.
No, go ahead.
I was listening to earlier, Ines, and you were talking about the study from China where they were talking about embedding that information that was non-digital, correct?
Yeah. Yes.
And that it reminded me a little bit of the Hawking description of what's happening in the information, how it's laid down in the center of black holes, on the edge in black holes. Is that correct? And
yeah, it could be related. Yeah, I think it is related. Yes.
But I'm also hearing that at the same time, and I tend to be kind of a visual person, a visual learner, and so I try to represent it visually. And I also want to comment on all of us. I see you, Ines, when you're looking for information, your eyes go up and go to the left and go to the right. You access information. I'm saying that you see it. I'm saying that that's an example of how the body, the mind, the consciousness accesses what Bill is talking about is a space-time memory network. Your consciousness, our consciousness is our body's ability to access that space-time memory network and to access those little bits of information that we have laid down within the fabric of space-time. Because I spoke with you in December and you said that we actually the Feynman links are actually bent or changed a little bit, and that we leave that information within the fabric of space-time on a four-dimensional map of our lives, much like a 78 or a 45 RPM record, the old style. And that information is old style, is analog. And so I would suggest that when Bill, when William, and I think William, you're really onto this here. You and Nissan is onto this, because what you're suggesting is that the mind is really a receiver of consciousness, and that we're a little bit like the primitive person who has never seen a radio and is listening to Beethoven's Ninth, cracks the radio open to look for the instruments inside, when in fact we're receiving that information. And I would suggest too that information is not, as Penrose says, it cannot be algorithmic, because when it comes to information systems, they will always spin out without novelty. They will always spin out of control and go to an excess, or to I'm losing the term, where information systems just spin out. So what I'm suggesting is that asking, about consciousness is that we are receivers of consciousness, and the consciousness that we experience is contained within our body, but it also is accessed from an area outside of our body, within the fabric of the ether of the space-time that we occupy.
Well, I think that one of the biggest revelations that will come within a science of consciousness is that we are actually within our consciousness.
Yes.
It's not, consciousness is not something that's within our brain. Our brain is within consciousness. I think, and its primary function is as a receiver.
Yes.
It's a fractal antenna and a transmitter with reply back functions. So I think that'll be one of the biggest breakthroughs in understanding in terms of a science of consciousness.
And to be able to move to that non-duality
Mhm.
position of consciousness,
Mhm.
that's a holistic, everything is connected non-duality view of consciousness, because by moving to a non-duality view, we cannot not see our connectedness with everything and all of the universe and all of those around us. It eliminates the objective empirical. I can own it. It's separate from me. I can kill it. I can do whatever I want to it. I can physically do this. But when you access a non-duality form of consciousness, you're doing it to yourself. Does that make sense then?
Yeah, it makes a lot of sense. I
really appreciate you guys. I thank you.
Yeah, Mike, this is a great intuition you had with black holes, because in fact, exactly that's what's happening. This holograms are created. That's why when you have a black hole, you have the event horizon is taken as the big principle. It's exactly because of that. So your intuition was right on it. It's that's why they're all black holes finally at the end. That's the way the information is being packed and it's being coded. No, but these are quantum bits. So this brings me to the next question you had, where you're saying that it from bit from Wheeler, then let's suggest that spin plus bit equals it, and that's an interesting way to put it, because this computation. Okay, so these are not. Okay, so you have we could see a black hole as a quantum computer. That's how I see it, in fact. And part of my research is going in that direction. I mean, it's like the proposal that each PSU is a quantum of consciousness. Each PSU is a particle of consciousness, but it is processing information, quantum information from the inside, and it's given an output of 0 or 1. It's digital to the outside, and it's quantum to the inside. It's a quantum superposition, but not in the sense I have even defined the kind of entanglement that would happen within, which is called the Coriolis entanglement. Coriolis because it's a double torus dynamics. So the symmetries and the algebra that corresponds to that, it's what I call Coriolis because of the double torus dynamics and that. It's a particular entanglement. So and it brings also a notion spin, because it's kind of like having this double spin. It's got all the elements, like you need chirality, you need this two sense directions to the inside out and outside in. That's also considered in this kind of programming. And now that brings me to the comment that Willem just did. There's a way of programming that so that you can have kind of an observation or an interpretation where this qubit, this quantum, it's in fact a particle of consciousness. It's a quantum of consciousness, which is, I'm preparing also an elective on that, but I haven't finished it. And so the origin of spin, because there are two origins of spin. You have density gradient, okay, which is what happens, like for instance, when the proton escapes this universe and creates a new one. And so you have this expansion without like a balloon. It's like it goes like, it expands like that. It's like, it's not a balloon, like, because you have the proton is spinning. So when it escapes the former universe, it comes out and it spins like that. It spins like that, and so there's other momentum which is being which is creating this density gradient as well. It's a contribution to the density gradient. So when the former larger universe is building up, you have this change of density, huge amount of density, which is the vacuum catastrophe problem, in fact. And that gradient of density, this density gradient, is what creates spin. It's the source of spin, no? But there's also, so everything is spinning inside, no? Everything which is contained in this larger volume, which is like, let's say, the universe, it's having this this rotation, this energy of rotation.
Can I interrupt for a second? I'm just smiling as you say that, because what you're describing is a double torus. What you're describing is a torus shape that's moving through space-time, that has movement and fluidity, and that spins at different direction, that incorporates two different spins within it. Is that what I'm hearing?
Yeah.
So the universe seems to replicate that function and form almost everywhere, doesn't it?
Yes, but you have also another situation, which is kind of what I'm trying to understand. And there's like the origin of spin. It's like there's also like a philosophical part to it, where the fact that how can I say that? When there's kind of an origin of spin, which is not a mechanical way of originating. It comes directly from, let's say, consciousness. Like a driving force where you would have, how to explain that?
Everywhere, all at once.
Yeah. It's like, no, it's like you have, it's like, you have to define like a frame of separation in order to see this. You know,
Okay.
when we see reference frames, when we talk about relativity, when we describe anything, whatever we have to define a reference frame. But this reference frame is mostly about separation of contrast. We say this is with respect to that. This is with respect to that. You know, there's always a contrast. So that's where duality and all that would come along. But basically, I think this is something which is fundamentally like that. Like that's a fundamental structure in for the universe, like that. So in the way it takes information. When you talk about information, we are talking about contrast, because if you have complete homogeneity, everything is completely homogeneous in all senses, then you have no information. So in order to have information, you need contrast of something. So if you have a contrast, then you have a comparison. You have a difference
that makes a difference.
Yeah, if you have this differentiation, then you have a frame of separation.
Yes.
Right? Right. Okay. Now
it's artificial. It's artificially created. We've decided that.
Yeah, it is. It is kind of. It is subjective.
Yes.
Okay. It is, but it's not artificial. It is subjective, and I don't know how. But this. No, that's the thing. When I got into this is how I got to know Nassim's work, and this is why I connected with. When I knew Nassim's work, I was working on something with my PhD, which was describing light matter interaction through a different mechanism, which was not quantum chromodynamics or anything like that. This is a very simple way of describing interaction through other mechanisms. And so I found this double torus dynamics using quantum mechanical concepts, like. And that the thing is that double torus dynamics was derived by Nassim and Elisabeth Rauscher through the solution of Einstein's fields equation inserting torque, which is the other side of the scale. You know, quantum mechanics is supposed to happen only at this inversional scale, and this is supposed to be the other, you know, the other regime. Yes. So suddenly you had the same solution for very different systems, and that's, for me, that was like a huge, like, wow, this is unification of forces, fields, and all of that from a very, very naive perspective, a very innocent, naive perspective. So that's how I got into Nassim's work, and then I saw the holographic solution, and then I realized that maybe these Plancks we're having the same dynamics. But what I was finding is that there's an irreducible representation of information exchange that is not reducible more than that, and that it concerns 4 situations that are connected and then create the double torus dynamics. And this double torus dynamics has an inwards force and an outwards force, which is the
Yes.
spin inside and to the outside.
Mhm.
So, so that's incredible, because I'm just using concepts of quantum mechanics and a little bit of logic, let's say, like you have to have some sense of logic here. That's all. So then you find the same solution. So that means that there's a part of the spin which is directly related to consciousness. Meaning by consciousness, the lack of an absolute frame of separation. This is a weird way of defining consciousness, but it's one of the definitions I have found for it. It's the lack of an absolute frame of separation. So you birth reference frames because you need to build the complete reference frame because there's this lack of an absolute frame of separation. And
I need that separation for I amness, to feel I am.
For the individuation, so this is another way of rephrasing is saying that the reference frame of observation is on the boundary conditions on the event horizon. So where's the observer located? It is located in this boundary condition in the event horizon of the black hole. That's where the observer is located. And so it's another way of saying the same thing. So I'm sorry I'm going into things.
No, it's a joy to hear the two of you, the energy that you have about this topic. And I appreciate you taking the time with me on this, because it's, I've studied consciousness for years now, 30 years now, as a counselor and as a family systems therapist. So teaching my students how to be aware and conscious in the here and now allows them the ability to act with hope and in a better way within the relationship. But the only way I can be aware as a counselor of how to best help people is to be fully conscious of myself in my body in the here and now. But so what I'm also looking at as consciousness is the ultimate unasked question, the ultimate unasked problem in science and physics and philosophy and in our lives. So I appreciate you taking the time to talk about this, because it's a big deal. And also it will affect, I think it affects biofield healing. All of this is all connected, and you guys are in the forefront of this. Thank you.
Oh my God, thank you. Thank you, Yields. Thanks. Okay.
So I saw a question here from Simon that I thought was very interesting. Considering ourselves within the new science as light beings at the Planck scale, do our cells have biophotons in communication with each other, which within each cell to create coherence? Do our cells emit light constantly, sending and receiving information faster than the speed of light, not visible to our eyes, yet similar bioluminescence? If so, how does this interact with the DNA? So there's a couple of important concepts to address. First, on understanding the role of light in the biological system. So, we can talk about biophotons, but it needs to be made clear that a photon is a photon. So whether it's being generated in the cell or by a light bulb, it's the same kind of photon. So, when we say biophotons, we're just referring very specifically to light being generated within the cell. And indeed, this is occurring constitutively all the time. Now, another important consideration is the relevance of describing light in its discrete descriptor, that is, as a photon, or in a form that is much more fluent, and I think actually better describes the behavior, which is its wave-like properties, its field-like behavior. Using photons as the descriptor for electromagnetic radiation, it makes good sense when the wave, the electromagnetic wave that you're describing, is extremely small. Examples of that would be light in the ultraviolet spectrum, in the X-ray spectrum, in the gamma ray spectrum. There, your wavelength, your little Planck vibration oscillation of the Planck field is really small. So it actually has particle-like properties to it. It actually very much appears as a particle. But you can take that same light, that same electromagnetic radiation, and stretch it out, decrease the frequency, increase the wavelength, and you can make it kilometers in size, and then you're talking about a radio wave. But at that point, the relevance of describing it as a photon kind of goes away. You don't really get a whole lot of use out of describing a radio wave as a photon, even though you can do that. But really its behaviors and how you're going to describe it, even mathematically, is going to be as a wave and a field-like interaction. And I mention that because for the biological system, the most important ranges within the electromagnetic spectrum, the most important frequencies and wavelengths are generally outside of that region where you'd be well served with a photon type description for the behavior of light. So within the biological system, optical light is playing a very significant role within the optical range, but much of the information transmission and communication that's happening in the cell and intercellularly is in the microwave, millimeter, or infrared, millimeter and microwave range frequencies of the light, and even our interaction electromagnetically with the environment. It's very possible that a really significant level of that interaction is happening in the radio wave frequency, for instance, with the Schumann resonances. So those are electromagnetic waves that are the size of the Earth's ionosphere. So that the ionosphere acts as a resonance chamber for those waves, and you get the Schumann resonances. But it's very interesting that they have peak values at 7 and 11 hertz, 18 and 22 hertz, 33 and 40 hertz. That's alpha, beta, and gamma brainwave oscillation modes too. So kind of interesting. Makes me wonder if maybe there's a connection there. So certainly, our 7 hertz brainwave oscillations are feeding the Schumann resonances. So that's an interesting thing. But what we're talking about there is a field-like activity, which I think is actually a better descriptor to understand what light is doing in the cell with the field-like behavior. Now, because of this constitutive electromagnetic activity of the cell, we are not just in the sense of what we understand from the Planck scale, we are light beings. So light is instrumental to all of our cellular functions, cellular growth, replication, encoding information, exchanging, transmitting, and communicating information within the cellular environment. So, you can point to very specific regions within the cell where this kind of light generation is happening to a large degree all the time. So like in the mitochondria of the cell, where you have a very high energy environment, that's where the adenosine triphosphate ATP molecule is being generated, which is a quantum entangled molecule, but that also carries not only that quantum entangled information, but also energy, chemical energy for the cell. Part of the process involved there is generating a large amount of biophotons within the microtubules, which if you follow certain ideas like Penrose and Hameroff's orchestrated objective reduction model for quantum consciousness, microtubules are a primary region within the cell, a primary structure within the cell that is being investigated for its role in information dynamics, particularly in generating consciousness and even intelligence, cellular intelligence and organismal level intelligence. One of the things there, you can have coupling of the water within the channel of the microtubule. The microtubule is a cylindrical tube, and within it is this atomically ordered water. That's liquid crystalline water. And liquid crystalline water has really interesting properties. Even bulk water has really interesting properties. Water in confined nanospaces does really phenomenal things, non-trivial things, even above and beyond the already really interesting properties of water. But one of the things that can occur is that the electric dipole moments of the tubulin all along the microtubule wall, they can couple via electromagnetic interaction. And this coupling is where you start to get that orchestrated objective reduction phenomenon, orchestrated behavior. They're coupling via the electromagnetic field. They can then couple as well to the water, that atomically ordered water channel within, and that begins to generate electromagnetic waves. And it's been shown that microtubules and mitochondria can act as optical waveguides so that they can actually harness and directly transmit these electromagnetic waves, much like a fiber optic cable. So they're optical waveguides, electromagnetic resonance chambers themselves. To harness and transmit this light. And this kind of induction is of coherent light. So the light has a very specific spin orientation, which at the start of the discussion we were discussing the importance of that.
Yes, yes.
And it's very similar to laser light. And we know the importance of laser light in information-based technologies. You read a CD-ROM with a laser, you encode information in a CD-ROM with a laser. For holographic information, you encode information in a hologram with a laser, and you retrieve it with a laser or incident light. So your coherent biolasing can generate electromagnetic waves in the mitochondria, in the microtubules that are acting as optical waveguides. It could be transmitted, for instance, to the cellular membrane, where you have delocalized electrons along the phosphate layer. And it can be imprinted, the information can be imprinted and recorded in those electrons holographically. So you can have a holographic information encoding via the coherent light being generated in the cell. And you'd also mentioned, is this occurring faster than the speed of light? One of the things is that within the microtubule, as those optical waveguides, you have what are called evanescent modes. And so that this is where it's important to have the description of the light as a wave. And so evanescent modes has to do with wavelengths that are transmitted through the microtubule that shouldn't be able to be transmitted through the diameter size of that optical waveguide. And one of the things that is known is that these evanescent modes are transmitted superluminally, faster than the speed of light. So, there's a lot of interesting potential ways that nature has harnessed light and is using light within the cell, biolasing, generating highly coherent light with specific single spin orientation, the transmission of these evanescent modes, which potentially occurs faster than the speed of light. And just one other part to answer your question on like how, for instance, this can interact with the DNA. Well, one of the most important aspects is that when the DNA is interacting with the nanomachines, the enzymes, the catalysts that read the code of the DNA, either to generate gene transcripts or to replicate the DNA, the way that they're communicating is via the electromagnetic field. That field-like information of the quantized electromagnetic field is being transmitted via the medium of liquid crystalline water between the DNA and the enzymes that are going to read the code of the DNA, either for replication or for generating gene transcripts. So that's a very important mechanism. But say that, the light being generated within the mitochondria or the microtubule network, the mitochondria, what's called the mitochondrial reticular matrix. If this light is incident upon the DNA, it can induce conformational changes. So DNA has different levels of information encoding. There's the linear nucleotide sequence, which is very important and well known, but it also encodes information in a spatio-temporal sequence of three-dimensional configurations, really four-dimensional configurations, because it's not only how the DNA folds in three-dimensional configurations, but also how those evolve in time. A lot of the so-called non-coding DNA, it's not coding for proteins, so it's not that linear sequence, that two-dimensional sequence that's important for the coding of information. It's coding information in spatio-temporal patterns in 4D. And so much of what that non-coding DNA is doing is folding into very specific configurations. And these are going to change the electromagnetic resonance of those regions of the DNA molecule. And so this can be used to store information or transmit information, and even modulate the activity of actual protein coding sequences, because depending on how these intergenic regions fold, they can open up certain gene regions to be expressed, to be read, or close them down. So that's one way that this light is interacting with the DNA, is that the DNA is changing its molecular configurations to modulate electromagnetic signals that it's sending out. and electromagnetic signals that it's receiving can shape these spatiotemporal configurations of the DNA.
Wow, thank you. It really unpacked. You remember you mentioning something about light in the cells a while ago in one of the discussions with Ines, and I got to listen to this like 50 times to follow all of that. Is the anatomically ordered water replenished through that one little tiny tube that one of you or Nassim talked about, that the cell can only get actually hydrated, I don't know if I'm saying this right, if the water has a certain structure that it can go into that, or does that anatomically ordered water always stay in there once the cell is generated? Does that make sense?
Yeah. So, there's some thought around the ability of water to enter into the cell. There's an immediate barrier to environmental water getting into the cell. Because, first you've got the plasma membrane. Now this is a fluid membrane. That's why it's called plasma. Plasma means fluid in Greek or Latin or whatever. But it's a plasma membrane, a fluid membrane. But it has what's called an inner hydrophobic core. So hydrophobic means that it doesn't like water and water doesn't like it. So you've got kind of an immediate barrier that is a fairly significant resistance to water coming into the cell. Now, some nevertheless gets through because it quantum tunnels right into the cell. There's a lot of that kind of activity going on within the cell. Things are not occurring in a linear fashion. It's all very non-linear. A lot of the molecular behaviors and activities down there. But then there's the aquaporin channel, which will facilitate water coming in. But then you've also got a secondary barrier because all along the cellular membrane, there is highly ordered liquid crystalline water along the surface of the membrane. And so like this is known through the work of, for instance, Professor Jared Pollack of the University of Washington. And he coined the term exclusion zone water, EZ water, to describe this liquid crystalline phase of water, this fourth phase of water. And
one of the reasons what that is. Yeah, I heard of that. Mm-hmm.
And one of the reasons he calls it exclusion zone water is that he was able to demonstrate its existence via its propensity to exclude large solutes. So you can actually observe, we've done it, I've got a couple microscopes to my side here, we've observed it here in the lab. You can actually observe the formation of this liquid crystalline water by putting in a tracer into your water, little micron spheres that you can see through a microscope. And when you form this exclusion zone water, you'll see those micron spheres being pushed out of the liquid crystalline phase. And so you can see this easy water. And it's just that the water is behaving a little bit more like a solid, a little bit more like a crystal than the liquid. Now, within the biological system, you have that all over the place, this liquid crystalline water and around the plasma membrane. So there's another region where it's a potential barrier. And so probably only water of very specific phase and a very specific energy can incorporate into that easy layer and get into the cell. So that's one of the things that we had discussed previously. And, it raises the question, well, if you're drinking water that is structured, or at least more structured than normal bulk water, perhaps that would facilitate hydration, intercellular hydration, because that water will be more readily incorporated into those easy zones, the liquid crystalline water of the biological system. Now, for the atomically ordered water in the microtubules, it doesn't really need to be replenished just because, those microtubules are forming within the cytoplasm. So, when they form, they can only form in the presence of water. So they're always incorporating in that water channel in the center whenever they form. They can't undergo the polymerization process without being in that cytoplasm environment. But one of the really interesting things that was done, and this is by a researcher who just does really fascinating work, Anna Bandyopadhyay. He's a visiting professor at MIT. Actually, me and Nassim visited him there in MIT, but he does a lot of work with electron microscopy at Tsukuba in Japan. And one of the things that he did was isolate a single microtubule from a brain cell, from a neuron. He put it between two gold electrodes, a single microtubule, and investigated it with his electron microscope. And so he's passing voltage, electrical current, through the microtubule via these gold electrodes it's attached to. And he shows that it has like a non-linear conductance of the voltage. So like the voltage was higher at the terminal end of what was inputted in. So it's like there's properties that are very much like that you see with like a superconductor type materials, quantum type materials. But one of the interesting things he saw is that when he removed that atomically ordered water channel from the center of the microtubule, when he dehydrated it, all of a sudden it lost all non-classical behavior. It started acting like a very conventional classical material.
Wow.
So actually more like an insulator even than a conductor for some of the voltage readings he was doing.
Yeah, thank you. Because I got I have the art crystal for several years now, and that I think you just distinguished between anatomically ordered water and highly structured water. And so I was wondering if that was assisting the water that I charge with the art crystal is assisting hydrating the cell or not. Yeah.
There's good reason to believe that it is assisting in hydration. And some of the testing that we've done has corroborated that idea. And that if you have plants that are given this water, that other tests have indicated is structured, they have drought resistance. They don't need as much water. They can do more with less water, and they can go longer periods of time without water. We definitely believe that this is an effect that we're seeing with that particular technology.
Yeah. Thank you.
Thank you.
That what you were talking about, William, about this like molecular transfer, it's like a molecular circuit where you would have conductance through this microtubule. Was it the circuitry microtubule? And would you see quantum current? I mean, quantization of the current. Would you see like current going on in steps? Did he show something like that?
I don't recall him discussing specifically quantization of the current. But I'm sure that information is available because, one of the things is that you're getting conduction of current electrons through many macromolecules, biopolymers like the microtubule, like DNA, even certain proteins, protein chains, polypeptides. You're getting conduction through them, even though in a conventional sense, they're insulator molecules, and the way that this is being achieved is via the quantum tunneling. That, even though classically there's a fairly significant resistance to the conduction in these biopolymers, these macromolecules, because it's quantum conduction, it's occurring via quantum tunneling, they can readily conduct current or electrons. And actually, they can do it better than a copper wire because they do it with ballistic conduction. I mean, it's like nearly a superconductor. The way that they're able to harness those quantum properties, that quantum tunneling, to have nearly 100% efficient transmission of this energy and the information of the signals. And, you know, it probably evolved from a really practical, pragmatic need within the cell, just that it needs to transfer energy. It needs to transmit information, which is energy as well. But it needs to be able to do that without generating a ton of heat. Now, if you think about, you know, our information technologies, it's a cell phone, your computer, when it's transferring information, storing information, it gets hot. You know, your computer needs a fan to cool down. So, you know, the biological system is kind of limited in what it can do to disperse all that heat that would be generated from all that information processing activity. So what it does is, what it discovered at some point early on was quantum tunneling. Well, let's just transmit these through the quantum wormhole network. Then we get nearly 100% efficient energy transmission, information transmission, and you're not generating a ton of heat, which would make the cell denature, fall apart.
Yeah, okay. I remember when I was working in molecular conductance, because the reason I asked this is because I did theoretical modeling of this kind of systems. You would have a molecule which is not a real molecule, it's a theoretical molecule, and you would have it coupled to two metallic points, and then you would have some voltage applied, and even you can induce some current with a laser, with lasing, also with electromagnetic fields and all of that. And I remember that when you had so the thing is that you hope between sites, because it's like a resonant condition. It's going through resonances inside the molecule, because when you modulate the voltage, you're having, like, normally they're not, you can, like, very roughly speaking, you can have the molecule depicted as atomic sites that are ones, and these sites are not at the same energy level. So that would be like impeding the current to flow. But if you modulate them, then you have some kind of, like, they get into a position in an energy level. Well, you could have the electron hooping from side to side. And so it is not exactly tunneling. It is kind of it tunnels, but it's driven by resonance. So you need this hoping, yeah. So through
You know what that sounds like to me is a saltatory conduction.
What's that?
Saltatory conduction. It's one of the ways that they describe the conduction of current within neurons. So along the neuronal axon, if you look at how the current is conducted, it's not linear. What it does is it jumps along the axonal membrane, and they call this saltatory because that's a Latin word for jumping. Saltatory.
You know, that's the thing. Now I remember, you have, in order to access all the sides and have the electrons go to the other side of the other electrode, let's say, you have to be turning, like, if you have a simple plot of current versus voltage, and you have a molecule, say, with 5 sides, that you would say would have to go through 5 sides to go to the other side. This is what you would have. You would have, like, kind of jumps like that in the current. So you have to increase the voltage in order to have so you have current versus voltage here. So this is voltage, this is current, and then the current would go like that by increasing the voltage. That's the quantum conductance. That's the quantization of the current. So that's what a molecule does. If you're going to have current going through a molecule, that's what, and you can have the same thing with a static voltage and using a laser, because the energy of the laser, if using a light as a source of light, because by changing the frequency, you can have the same access. You can have, you give more energy to electrons, so the electrons can go into these different energy levels, and that's how the electrons go to the other side. And in some conditions, you can have a total ballistic, but that's a specific conducting kind of a situation, which is not common. It's not the common thing is to increase voltages so that you could go all the way into the whole to the other side, let's say, to the other side of the. So I would like to see those experiments from this Japanese guy.
Yeah, I'll have to.
PhD on. I mean, that's the topic I did my PhD. It's molecular transfer in molecular wires assisted by light. So yeah,
I'll have to go back to the papers and see if he mentions.
What year was that? That
What's
you went? What year was that? That you went to see this guy in MIT? What year was that?
2014, I think. Yeah,
Oh.
2004. It might have even been 2013. So
Oh my God.
maybe 10 years
Okay.
ago.
That's
Yeah.
That's
But
great.
you know, he's just a very let's say avant-garde researcher. So you know, he was following Nassim's work, and
Oh, that's interesting.
he heard that Nassim was speaking with the head of the physics department there at MIT to share his, at that point in time, recently discovered quantum gravity solution, the holographic ratio there.
Yeah.
And he invited Nassim to come and speak, and I had been following Andrew Bond's work for some time, so Nassim said, "Okay, you're familiar with his work. You come with. We'll go talk to him." Yeah.
Oh my God, awesome. That's great. Okay.
Yeah. Well, so we're out of time. It's been 2 hours already. I can't believe it.
Yeah.
There's still so many great questions, but hopefully we can save them for the next session, the next faculty Q&A session, and we can just dive right back into these discussions here. Thank you all so much for joining us. Always a great time getting to discuss these concepts with you, and we'll be
I'm a
having.
little bit curious. There's someone who's raised his hand. I think, do I know that person? Maybe we could, because I think it's trying to communicate. Venice Inventors.
Oh yeah. Did you want to?
Yeah, maybe just to know.
See,
But
ask real
I
quick.
won't be able to see. I won't be able to see this person because I'm not sure I know this person personally, and I have been reading some messages, and so I don't know exactly. But I cannot see the person. So Venice Inventors.
Yo en España.
¿Quién es? Hola. Aló. Oh, I don't hear.
I heard them for a moment there.
Yeah.
Well, Venice Inventors, join us next time, and we'll bring you up.
Yes.
So yeah, we'll be having another session in March. So we'll look forward to seeing you all there.
Yeah.
Hola.
Hola, ¿cómo te llamas?
Me llamo Alexandra y yo tomé la clase de Unified Science for Kids.
Qué gusto.
Sí, estuvo increíble. Should I speak in English or Spanish? I'm sorry.
Okay, no worries. I just wanted to know where I knew you from. Thank you.
Ya, soy peruana, Serbia, crecí en Perú y en Serbia y ahorita estoy aquí en Los Ángeles y estoy tratando de estudiar con ustedes ciencia y ustedes me inspiran tanto y son increíbles y me encanta como la pasión y la energía que le ponen a este tema que es tan interesante y que se necesita, y sobre todo mujeres, ¿no? En esta parte de la ciencia.
Ok, gracias.
Thank you so much.
Thank
I
you.
do have a quick question. I don't know if I could ask.
No, I think for the next time, yeah.
Okay, perfect.
Yeah.
Thank you.
Thank you, thank you. Thank you so much.
I'll see you all. May the vacuum be
Well,
with you.
See you all the next time.